Between your fingertip and whatever it rests upon, a pillow, a page, the familiar warmth of another hand, there exists a gap so small that no instrument has ever measured its crossing, and yet nothing in this universe has ever truly closed it. This is the quiet truth that physics holds like a secret, the knowledge that all contact is an illusion woven from invisible forces, that the atoms of your body have never once touched the atoms of anything else, separated always by an infinitesimal ocean of empty space and electromagnetic refusal. If these gentle explorations help carry the mind toward rest, subscribing means more nights like this one will find their way to you. What follows is a slow wandering through that impossible distance, through the quantum void that hums between all matter, between every embrace that ever was, and here, in the stillness, we begin. When you place your hand upon a wooden table, there is a familiar sensation that arises, a feeling so ordinary and so constant that you have likely never paused to consider its deeper nature. The surface meets your palm with what seems to be perfect contact, the grain of the wood pressing gently against your skin, and your mind registers this as the most basic form of knowing, the simplest confirmation that the world beyond your body is real and present and waiting for you. Your fingers might trace across the grain, feeling the slight ridges where the tree once grew ring after ring in some quiet forest, and each tiny variation in texture sends signals through your nerves that speak of solidity, of there-ness, of a universe that can be relied upon to push back when you push against it. Consider now the experience of settling into bed, as perhaps you are doing at this very moment, and the way that cotton sheets feel against your skin when you draw them up toward your shoulders. There is a softness there, a gentle yielding quality, and yet beneath that softness you can still sense the presence of fabric, of threads woven together by machines or by careful hands, of matter arranged in patterns that your fingertips can dimly perceive even without looking. The sheets do not pass through you, and you do not pass through them, and this mutual resistance between your body and the bedding seems like the most natural thing in the world, a fundamental truth that requires no explanation because it has been true for every moment of your life since the very beginning. This experience of touch, this immediate knowledge of physical contact, held a position of supreme importance in the philosophy of the ancient world, and nowhere is this more carefully examined than in the writings of the Greek philosopher Aristotle, whose treatise on the soul, composed around 350 years before the Common Era, devoted considerable attention to the senses and their role in human understanding. In that work, which scholars have come to call de anima, Aristotle argued that touch was not merely one sense among equals but rather the most fundamental of all the ways that living creatures come to know the world around them. He observed that while a creature might lack sight, as many that dwell in darkness do, or might lack hearing, as certain simple organisms seem to, no animal could exist without some capacity for touch. For it is through touch that we know whether something is hot or cold, hard or soft, and whether it might nourish us or cause us harm. Touch, in the Aristotelian view, forms the very foundation upon which all other sensing is built, the bedrock sense that connects living matter to the matter that surrounds it. Many centuries would pass before another great thinker would take up this question of touch and its philosophical significance, and when he did, he would anchor his entire theory of human knowledge upon the simple experience of feeling the world against your skin. The English philosopher John Locke, writing in the year 1689, produced a lengthy work entitled An Essay Concerning Human Understanding, in which he attempted to trace the origins of every idea that the human mind can entertain. Locke was troubled by skeptics who suggested that perhaps the external world did not exist at all, that perhaps everything we seem to perceive is merely a dream or an illusion conjured up within our own minds, and he sought to find some firm ground upon which certainty might stand. For Locke, that firm ground was touch. For when we feel the resistance of objects against our bodies, when we experience what he called the solidity of matter pushing back against us, we receive a kind of evidence that goes beyond mere appearance. A visual image might deceive us, as anyone who has seen a mirage or a clever painting knows. But the sensation of one solid thing pressing against another solid thing carries a weight of reality that imagination alone cannot counterfeit. When you tap your knuckles against a tabletop and feel that gentle resistance, you are, in the Lockean view, conducting a small experiment that proves the table exists outside of your mind. This comforting philosophy of touch, this notion that matter is straightforwardly solid and that our fingers bring us accurate reports of its solidity, found what seemed to be perfect confirmation in the scientific developments of the 19th century, when great progress was made in understanding the nature of the tiny particles from which all material things are composed. The scientists of that confident age imagined atoms as very small but essentially simple objects, like miniature billiard balls that bounced against one another according to the ordinary laws of motion, possessing definite sizes and definite shapes and definite positions in space at every moment. This picture was deeply satisfying because it matched so well with everyday experience, suggesting that the solidity you feel when you touch a table is simply the cumulative effect of countless tiny balls packed closely together, each one as solid and impenetrable as a marble, each one occupying its own small region of space and refusing to allow anything else to occupy that same region. One particularly elegant version of this mechanical picture was proposed by the Scottish physicist William Thomson, who would later become Lord Kelvin and who was one of the most celebrated scientists of his era. In the year 1867, Thomson presented a theory suggesting that atoms might be understood as tiny vortices, like minuscule whirlpools, spinning within an invisible medium called the ether that was thought to fill all of space. He had been inspired by observing smoke rings and the remarkably stable way that they maintain their shape as they drift through the air, and he wondered whether atoms might be something similar, self-sustaining patterns of rotation in a universal fluid that would explain their permanence and their consistent properties. This vortex theory of matter was for a time taken quite seriously, and it offered a vision of the physical world as a kind of vast clockwork mechanism, intricate but ultimately comprehensible, built from components that behaved in predictable ways that any careful student might hope to understand. The confidence that Thomson and his contemporaries felt in their mechanical models of nature found clear expression in a series of lectures that he delivered in the city of Baltimore in the year 1884. Where he spoke to audiences of American scientists about the present state of physical knowledge. In those lectures, Thomson expressed his belief that the fundamental phenomena of nature would eventually yield to explanation in terms of ordinary mechanical forces, the same pushes and pulls that govern the behavior of gears and levers and all the familiar machines of daily life. There was no mystery, he seemed to suggest, that could not be dispelled by imagining the right arrangement of particles in motion, the right combination of tiny solid objects bouncing and spinning and colliding according to Newton's ancient and reliable laws. This was a picture of reality that invited confidence, that suggested the universe was not only knowable but indeed rather sensible, operating according to principles that would feel natural to anyone who had ever pushed a cart or thrown a ball or felt the satisfying click of billiard balls striking one another on a green felt table. The deep intuitive comfort that we find in this solid, reliable picture of matter has roots that reach back far earlier than any philosophy or science, reaching back indeed to the very earliest experiences of our lives. when we first began to discover that we had bodies and that those bodies existed in a world of other objects. The Swiss psychologist Jean Piaget, whose careful observations of infant development conducted through the 1920s and the decades that followed would transform our understanding of how children come to know their world, described the earliest stage of cognitive growth as the sensoromotor period, a time when babies learn almost everything they know through the direct experience of touching and grasping and mouthing the objects around them. A very young infant will reach out a hand and feel the smoothness of a wooden block or the softness of a stuffed toy. And these tactile experiences become the building material from which an understanding of reality is slowly constructed. Piaget observed that infants must learn through repeated experience that objects continue to exist even when they cannot be seen, a concept he called object permanence. And this learning depends crucially upon the consistent evidence of touch, upon the reliable discovery that when you reach toward something that has disappeared behind a blanket, your fingers will find it still there, still solid, still real. Before language, before abstract thought, before any of the sophisticated intellectual machinery that allows adults to contemplate philosophy and physics, there is simply the hand closing around the rattle, the palm pressing against the crib, the mouth exploring whatever comes within reach. This is how we first come to believe in the reality of matter, and the lessons learned in those earliest months stay with us throughout our lives, forming the unquestioned background assumptions against which all later knowledge is measured. And so when you lie quietly and feel the gentle pressure of your pillow against your cheek, or when you reach out to adjust your blanket and your fingers find the edge of the fabric exactly where you expected it to be, you are participating in an experience that connects you to a long tradition of trust in the solidity of the physical world. The philosophers who argued that touch proves reality exists, the Victorian scientists who imagined atoms as tiny balls of matter obeying clockwork laws, the infant you once were who learned to trust the consistent feedback of your senses, all of these are present in some way in the simple experience of contact between your body and the material things around you. This is the baseline, the comfortable starting point from which humanity approached the strange discoveries that would emerge in the early decades of the 20th century, when careful experiments and mathematical reasoning would begin to reveal that the apparent solidity of matter is something rather different from what our senses suggest. But for now, there is only the gentle pressure of fabric against skin, the familiar feeling of your body resting upon a surface that holds you up as it has always done, the simple and ancient knowledge that what you touch is really there. The certainty of touch is a comforting thing, a feeling so deeply woven into our experience of being alive that we rarely think to question it, and it is natural to imagine that this feeling reflects some fundamental truth about the nature of matter, that the world really is as solid and reliable as it seems when you run your hand across a smooth piece of wood or feel the warmth of another person's palm in your own. This was the understanding that prevailed for most of human history, the working assumption of countless generations who built their homes and tilled their fields and went about their lives in confident reliance upon the solidity of the earth beneath their feet. It is an understanding worth appreciating, worth lingering over for a moment, before we follow the thread of scientific inquiry into stranger territories where the comforting picture will gradually give way to something more subtle and more surprising. For now, you might simply rest in the feeling of contact between your body and whatever surface supports you, noticing the gentle pressure and the familiar sense of being held in place by matter that feels entirely solid and entirely real. This is the knowledge that your fingertips have brought you since before you could speak, the evidence that Locke trusted and that Aristotle praised as most fundamental, the bedrock experience upon which our intuitive physics is built. Let it be a comfort as you settle further into stillness, knowing that whatever strangeness lies ahead in our slow investigation of touch and matter, this simple feeling of contact will remain, reliable as it has always been, asking nothing of you but your quiet attention. In the year 1911, in a basement laboratory at the University of Manchester, a New Zealand physicist named Ernest Rutherford undertook an experiment that would quietly overturn centuries of assumptions about the nature of solid matter. And in doing so, he would reveal that everything we perceive as substantial and firm is, in truth, almost entirely made of nothing at all. The experiment itself was remarkably simple in its conception, involving little more than a source of radiation, a thin sheet of gold, and a fluorescent screen arranged to detect where particles landed after passing through or bouncing off the metal foil. Yet from this modest arrangement emerged one of the most profound discoveries in the history of physics, a finding so unexpected that Rutherford himself would later describe his astonishment in terms that captured perfectly the magnitude of what he and his colleagues had stumbled upon in that quiet English laboratory. The two experimenters who carried out the day-to-day work of this investigation were Hans Geiger, a German physicist who would later lend his name to the radiation detector we still use today, and Ernest Marston, a young student who was only 20 years old at the time. Together, under Rutherford's guidance, they set about firing alpha particles at an exceedingly thin sheet of gold leaf, the metal beaten so fine that it was only a few hundred atoms thick, practically translucent to visible light. Alpha particles, as you may recall from earlier discussions or perhaps from long-forgotten chemistry lessons, are tiny bundles of matter ejected from radioactive substances, consisting of 2 protons and 2 neutrons bound together, and they travel at tremendous speeds, carrying considerable energy as they move through space. The prevailing understanding at the time suggested that atoms were something like plum puddings, a model proposed by the English physicist J.J. Thomson, in which negatively charged electrons were embedded throughout a diffuse sphere of positive charge, rather like raisins distributed evenly through a Christmas pudding. If this model were correct, then alpha particles fired at gold foil should pass through with only minor deflections, their paths gently curved by the distributed positive charge but never dramatically altered. What Geiger and Marston observed, however, was something quite different, and it was the careful attention they paid to an unexpected result that made their experiment so consequential. Most of the alpha particles did indeed pass straight through the gold foil as if it were not there at all, continuing on their trajectories with barely any deviation from their original paths. This in itself was slightly surprising given the apparent solidity of gold, but it was not the truly remarkable finding. The remarkable finding was that a very small number of alpha particles, roughly 1 in every 8,000, bounced backward, returning in the general direction from which they had come, as though they had struck something immensely dense and solid within the supposedly diffuse atomic structure. This backward scattering was so unexpected, so contrary to what the plum pudding model predicted, that Rutherford was genuinely astonished when Geiger reported the results. He would later write that it was quite the most incredible event that had ever happened to him in his life, comparing the experience to firing a 15-inch artillery shell at a piece of tissue paper and having that shell come back and hit you. The metaphor captures perfectly the sense of impossibility that these results conveyed, for if atoms were truly diffuse spheres of evenly distributed charge, then nothing within them should have been capable of deflecting those fast-moving alpha particles so dramatically. Rutherford spent considerable time pondering these results, and the explanation he eventually arrived at required a complete reimagining of atomic structure. The only way to account for the backward scattering of alpha particles was to propose that almost all of the mass of an atom, along with all of its positive charge, was concentrated in an incredibly tiny region at the center, a region so small that most alpha particles would miss it entirely as they passed through the atom, but so dense that any particle unfortunate enough to approach it directly would be violently repelled. This tiny region Rutherford called the nucleus, and his calculations suggested that it was approximately 10,000 times smaller than the atom as a whole. To put this in perspective, if you were to enlarge an atom to the size of a great cathedral, perhaps something like St. Paul's in London or one of those magnificent Gothic structures that took centuries to complete, the nucleus would be no larger than a common housefly buzzing somewhere within that vast interior space. The electrons, those negatively charged particles discovered by Thomson some years earlier, would be located somewhere near the outer walls of this imagined cathedral, leaving the enormous volume between nucleus and electrons entirely empty. This emptiness is worth dwelling upon for a moment, because it represents such a dramatic departure from our everyday experience of the world. When you rest your hand upon a wooden table or feel the weight of a stone in your palm, every intuition suggests that you are touching something solid, something filled throughout with material substance. Yet Rutherford's experiment revealed that the atoms comprising both your hand and the table are almost entirely vacant space, with all of their mass concentrated in those impossibly tiny nuclei that occupy such a minuscule fraction of the atomic volume. If you were to remove all the empty space from the atoms in your body, compressing only the nuclei together, you would be reduced to a speck so small as to be invisible to the naked eye, yet you would retain every gram of your original mass. This is the strange reality that the gold foil experiment unveiled, a reality in which solidity is an illusion maintained by forces rather than by substance, and in which emptiness is far more fundamental to matter than we ever imagined. It is worth noting that Rutherford's nuclear model was not entirely without precedent. For several years earlier, in 1904, a Japanese physicist named Hantaro Nagaka had proposed a model of the atom that bore some resemblance to what Rutherford would later establish through experiment. Nagaka called his conception the Saturnian model, because he imagined electrons orbiting around a central positive mass in the same way that the rings of Saturn orbit around that giant planet. The analogy was not perfect, and Nagaoka's model lacked the experimental support that Rutherford's would later provide, but it represented an early and insightful attempt to move beyond the diffuse, structureless atom that had dominated scientific thinking. Nagaoka's work was known to European physicists, though perhaps not as widely appreciated as it deserved to be, and the Saturnian model stands as a reminder that scientific progress often involves multiple minds reaching towards similar truths from different starting points, with the credit typically going to whoever provides the decisive experimental evidence. The implications of Rutherford's discovery were profound and somewhat unsettling, for they suggested that the material world is far less substantial than it appears. When we say that matter is 99.9999999% empty space, we are not engaging in poetic exaggeration but rather stating a straightforward mathematical consequence of the relative sizes of nuclei and atoms. The number of nines in that percentage is not chosen arbitrarily. It reflects the actual ratio of volumes involved when you compare the tiny nucleus to the much larger atomic sphere that surrounds it. This means that when you sit in a chair, the atoms of your body are not actually touching the atoms of the chair in any conventional sense. Instead, electromagnetic forces are keeping them apart. Forces that arise from the electrons surrounding those distant nuclei and that create the sensation of solidity without any true contact occurring. We will explore this phenomenon in greater depth as our discussion continues. But for now, it is enough to appreciate that Rutherford's experiment opened the door to this understanding by revealing just how empty atoms truly are. In the years immediately following Rutherford's announcement of his nuclear model, other physicists set about refining and extending his ideas. And perhaps the most significant of these contributions came from the Danish physicist Niels Bohr, who in 1913 proposed a more detailed picture of atomic structure that would come to be known as the Bohr model. Bohr accepted Rutherford's central finding that atoms consist of a tiny, dense nucleus surrounded by electrons at a much greater distance. But he added crucial details about how those electrons are arranged and how they behave. In Bohr's conception, electrons orbit the nucleus in specific paths, somewhat like planets orbiting the Sun, with each orbit corresponding to a particular energy level. Electrons could not exist at just any distance from the nucleus but were restricted to certain allowed orbits, and they could jump from one orbit to another by absorbing or emitting precise amounts of energy. This quantization of electron orbits, as it came to be called, was one of the founding insights of what would eventually develop into quantum mechanics, and it helped to explain various puzzling features of atomic behavior that Rutherford's simpler model could not address. The planetary analogy that Bohr employed, while useful for visualization, should not be taken too literally, and indeed later developments in physics would reveal that electrons do not orbit nuclei in the neat, deterministic paths that planets follow around stars. Nevertheless, the Bohr model represented an important step forward in understanding atomic structure, and it reinforced the essential insight that had emerged from the gold foil experiment, namely that atoms are mostly empty space with nearly all their mass concentrated in a central nucleus. This emptiness at the heart of matter would continue to inform and perplex physicists throughout the 20th century, leading eventually to the strange and counterintuitive world of quantum mechanics, where particles can exist in multiple states simultaneously and where the very notion of position becomes fundamentally uncertain. But all of that lay in the future when Rutherford, Geiger, and Marston peered at their fluorescent screen in that Manchester basement, counting the faint flashes of light that revealed where alpha particles had landed after their encounter with gold atoms. The gold foil experiment remains one of the most elegant demonstrations in the history of physics, a case where a simple arrangement of apparatus revealed something profound about the nature of reality. The results were reproducible and unambiguous, and they demanded an explanation that transformed our understanding of matter at its most fundamental level. Where once we imagined atoms as solid spheres or diffuse clouds of charge, we now knew them to be vast empty spaces dominated by electrical forces, with all of their substance concentrated in regions so small as to be almost imaginary. This emptiness is with you always, present in every breath you take and every surface you touch, and yet it remains invisible to your senses, hidden behind the convincing illusion of solidity that matter presents to us. The cathedral that is each atom stands mostly hollow, with its fly-sized nucleus holding all the mass that makes the world feel real. And it is this strange architecture, revealed in a basement laboratory more than a century ago, that ensures you can never truly touch anything at all. In the year 1924, a young French physicist named Louis de Broglie submitted a doctoral thesis in Paris that would quietly begin to dissolve the very notion of solid matter, and though the thesis itself was brief, running to just over 100 pages, its implications would eventually spread outward like ripples across still water, touching every corner of physics and changing forever how we understand the particles that make up our bodies, our beds, and the gentle darkness of the room around us as we rest. De Broglie, who came from an aristocratic family and had initially studied history before turning to physics, proposed something that must have seemed almost dreamlike to his examiners, suggesting that particles of matter, those tiny bullets we had imagined ricocheting through the void, might also behave as waves, spreading and undulating through space in a manner not unlike light itself. He arrived at this idea through a kind of symmetry, reasoning that if light, which we had long believed to be a wave, could also behave as particles, as Einstein had shown with his work on the photoelectric effect, then perhaps particles of matter might also possess this dual nature, existing simultaneously as both localized points and spreading oscillations. The committee examining his thesis was reportedly uncertain how to receive such an unusual proposal, and one member is said to have sent the work to Einstein himself for an opinion, whereupon Einstein responded with encouragement, recognizing in de Broglie's mathematics the seeds of something profound and true. This notion of matter waves, as they came to be called, would soon find experimental confirmation when electrons were shown to produce interference patterns, those characteristic stripes of light and dark that only waves can create. And yet even as this confirmation arrived, physicists found themselves grappling with a strange new question, wondering what exactly was waving. What substance or medium carried these oscillations through the emptiness of space? For with light, one could at least imagine some luminous vibration traveling outward from a source. But with an electron, a particle we had thought of as a tiny grain of negative charge, the nature of the wave remained mysterious, and it would take the work of other minds, working in other cities across Europe, to begin to shape an answer that was both mathematically precise and philosophically unsettling in equal measure. In the university town of Göttingen, nestled in the gentle hills of Lower Saxony, a physicist named Max Born was working through the implications of these new ideas in 1926, and it was Born who would propose an interpretation that shifted the meaning of the wave function away from anything we might visualize or touch, suggesting instead that the wave associated with a particle did not represent the particle itself, nor any physical medium through which it moved, but rather the probability of finding the particle in any given location. This interpretation, now known as the Born rule, told us that if we wished to know where an electron might appear when we looked for it, we should take the wave function, square its amplitude at each point in space, and the resulting number would give us the likelihood of detection, the mathematical odds of the electron manifesting at that particular spot when a measurement was made. What had seemed like a spreading physical presence was revealed instead to be a spreading of possibility, a ghostly distribution of maybes and mightbes that condensed into certainty only at the moment of observation. And this understanding, while it provided physicists with a reliable tool for making predictions, also opened a door onto questions about the nature of reality itself that have never been entirely closed. Meanwhile, in the Austrian city of Vienna and later in Zurich, another physicist was pursuing his own path through these tangled ideas, and Erwin Schrödinger, a man known for his deep interests in philosophy and his somewhat unconventional personal life, would in that same year of 1926 develop an equation that remains central to quantum mechanics to this day. Schrödinger's wave equation provided a mathematical description of how the wave function of a particle changes over time, allowing physicists to calculate the evolution of a quantum system with remarkable precision. And when applied to the electron in an atom, the equation revealed that the old picture of electrons orbiting a nucleus like planets around a sun was not merely incomplete but fundamentally incorrect. Instead of neat circular or elliptical paths, the equation yielded probability clouds, regions of space where the electron was more or less likely to be found, and these clouds took on shapes of surprising beauty, with some forming spheres and others forming lobes or rings or more complex geometries, all of them representing not the path of the electron but the territory of its possible existence. The electron, in this new picture, did not travel from one point to another in the way a ball rolls across a table, but instead existed in a kind of smeared-out potentiality, present everywhere within its probability cloud until the act of measurement caused it to appear in one definite location, after which the cloud would begin to spread again, the certainty dissolving back into possibility as time moved forward. In Copenhagen, a city of harbors and spires and long northern twilights, Niels Bohr was working to synthesize these various strands of thought into a coherent framework, and it was Bohr's Institute that became a gathering place for the young physicists who were reshaping our understanding of nature, a kind of intellectual refuge where ideas could be tested and debated in an atmosphere of collaborative intensity. Among those who came to Copenhagen was a young German physicist named Werner Heisenberg, and it was during his time there, in the year 1927, that Heisenberg would formulate a principle that strikes at the very heart of what we can know about the subatomic world, a principle that tells us certain pairs of properties cannot both be measured with perfect precision, no matter how sophisticated our instruments or how careful our technique. This uncertainty principle, as it came to be known, states that the more precisely we determine the position of a particle like an electron, the less precisely we can know its momentum, and conversely, the more precisely we measure its momentum, the more uncertain its position becomes. And this is not a limitation of our technology or our cleverness but a fundamental feature of nature itself, woven into the fabric of reality at the most basic level. The nights in Copenhagen could be long and cold, and Heisenberg later recalled taking walks with Bohr through the city after dark, the two of them wandering through parks and along quiet streets, debating the meaning of these new discoveries until the first grey light of dawn began to show over the rooftops. They discussed the nature of measurement and the role of the observer, wondering whether the act of looking at a particle somehow changed it, and they struggled with the implications of a physics in which certain kinds of knowledge were forever beyond reach, sealed away not by practical difficulty but by the structure of existence itself. These conversations, which often continued until both men were exhausted, helped to shape what would become known as the Copenhagen interpretation of quantum mechanics, a framework that accepts the probabilistic nature of the quantum world and refrains from asking what a particle is doing when no one is looking, focusing instead on what can be predicted and observed. The uncertainty principle, in this view, is not a sign of incomplete understanding but a genuine feature of the universe, a boundary beyond which classical intuition cannot pass, and accepting this boundary requires a kind of intellectual humility that does not come easily to those trained to believe that nature can always, in principle, be fully known. In the autumn of 1927, many of the leading physicists of the age gathered in Brussels for the Fifth Solvay Conference, a meeting devoted to the new quantum theory and its implications, and it was here that the debates that had been conducted in private, in Copenhagen and Göttingen and Cambridge, spilled out into the open, with the older generation of physicists confronting the strange new ideas that the younger generation had developed. Albert Einstein, who had done so much to launch the quantum revolution with his work on the photoelectric effect and the photon, found himself increasingly troubled by the direction quantum mechanics had taken, and at the conference he engaged in a series of discussions with Bohr that would continue intermittently for years, each man trying to convince the other of his view. Einstein famously expressed his discomfort with the probabilistic nature of quantum mechanics by saying that he could not believe God would play dice with the universe, a remark that captured his sense that beneath the apparent randomness there must be some deeper layer of reality, some hidden mechanism that would restore determinism and causality to physics. Bohr replied, with characteristic patience and perhaps a touch of weariness, that Einstein should stop telling God what to do, suggesting that our preferences about how nature ought to behave should not constrain our acceptance of how nature actually is. The debate was never fully resolved during either man's lifetime, and it continues in various forms to this day, with physicists and philosophers still arguing about the interpretation of quantum mechanics and the nature of reality at the smallest scales. One of the participants at that Brussels conference, a young Englishman named Paul Dirac, would soon make his own contributions to the developing theory, contributions that pushed the mathematics of quantum mechanics to new levels of elegance and abstraction. Dirac, who was known for his extreme quietness and his almost monastic dedication to physics, developed an equation that combined quantum mechanics with Einstein's theory of special relativity, and in doing so he predicted the existence of antimatter, a prediction that would be confirmed just a few years later with the discovery of the positron. In his writings on the nature of the electron, Dirac described it as a mathematical point with no spatial dimension whatsoever, a description that seems almost paradoxical, asking us to imagine something that exists and has properties and yet occupies no volume, takes up no space, and cannot be said to have a size. This characterization reinforces the strangeness that emerges from quantum mechanics, the sense that the particles which make up our world are not little balls or tiny grains but something far more elusive, entities that can be described mathematically with great precision and yet resist any simple picture we might form of them in our minds. If we gather all of these ideas together, allowing them to settle gently like leaves falling onto still water, we begin to see a picture of the electron that is very different from the one we might have carried with us from school science lessons or popular accounts of the atom. The electron is not a solid particle tracing a definite path around the nucleus, nor is it a wave spreading uniformly through space, but rather a kind of probability distribution, a cloud of likelihood that tells us where the electron might be found if we were to look for it, without committing to any particular location before the measurement is made. It exists, if we can even use that word, as a superposition of possibilities, a mathematical ghost that haunts a region of space until the act of observation causes it to crystallize briefly into a definite position, after which it begins to spread again, the certainty fading like morning mist under a warming sun. The solid particle we once imagined, the little bullet or billiard ball, has become something far more subtle, a presence that cannot be pinned down, a thing that is always partly elsewhere, always partly something else. And so, as you lie here in the quiet darkness, you might let these ideas drift through your mind without grasping too firmly at any of them, allowing the electrons in your own body to remain mysterious, accepting that the matter of which you are made is not the solid stuff it appears to be but something lighter and stranger, a collection of probability clouds overlapping and interacting according to rules that even the greatest physicists of the 20th century found deeply puzzling. There is something restful in this uncertainty, something that releases us from the need to pin everything down, to know exactly where each particle is and what it is doing at every moment. The universe, at its most fundamental level, keeps some of its secrets, and the electrons that make up your hands and your heart and the pillow beneath your head exist as smeared possibilities, ghosts of likelihood that coalesce and dissolve and coalesce again in patterns too fine for any eye to see. This is the disappearing electron, The particle that becomes a wave. The point that becomes a cloud. The certainty that becomes a probability. And it is, in its own quiet way, one of the strangest and most beautiful things we have ever learned about the world in which we live and sleep and dream. When you place your hand upon a wooden table, or rest your head against a pillow, or feel the gentle weight of a blanket settling across your body, there is something rather remarkable happening at a scale far too small for you to perceive. Something that has puzzled and delighted physicists for nearly a century now, and which reveals that the sensation of touching, of solid contact, of one thing pressing firmly against another, is not quite what it seems to be at all. Your hand, you see, never actually makes contact with the table in the way that we might intuitively imagine, never truly arrives at the surface of the wood, never achieves that final moment of absolute togetherness with the atoms that make up its polished grain. Instead, what you experience as touch, as solidity, as the reassuring firmness of the physical world, is something far more subtle, far more interesting, and in its own quiet way, far more beautiful than simple contact could ever be. The reason for this curious state of affairs lies in the behavior of electrons, those tiny particles that orbit the nuclei of atoms in clouds of probability, and which carry a negative electrical charge that makes them rather particular about the company they keep. When you press your hand downward onto a table, the electrons in the outermost regions of your skin's atoms begin to approach the electrons in the outermost regions of the table's atoms, and as they draw nearer to one another, something begins to happen, something that feels to you like resistance, like solidity, like the table pushing back against your hand. This is electromagnetic repulsion, the simple and ancient principle that like charges repel one another, that negative pushes against negative, that electrons, being all of them negatively charged, have no desire whatsoever to get any closer to other electrons than they absolutely must. This invisible pushback, this gentle but unyielding resistance, is what prevents your hand from passing through the table, what keeps your feet from sinking through the floor, what allows you to pick up a cup of tea without your fingers sliding through its ceramic walls. It is happening constantly, everywhere, in every moment of your life, and it operates across a gap so small that it might as well not exist for all practical purposes. And yet that gap is real, is measurable, is always there between you and everything you have ever touched or ever will touch. The distance is roughly 1 angstrom, which is to say about 1/10,000,000th of a meter, or if you prefer, about 0.1 nanometers, a measurement so tiny that it takes a certain kind of patient imagination to hold it properly in your mind. At this scale, you are always hovering, always separated from the world by this thinnest of cushions, this quantum breath of space that your electrons and the table's electrons maintain between themselves with perfect and unwavering diligence. The physicist Richard Feynman, who possessed a remarkable gift for explaining difficult ideas in ways that made them feel almost conversational, addressed this very phenomenon in his series of lectures on quantum electrodynamics, delivered in 1985 at the University of California, Los Angeles, to an audience of people who were curious about physics but who were not necessarily physicists themselves. In those lectures, Feynman explained that when you press your hand against a table, what you are actually experiencing is the electromagnetic force, the repulsion between the electron clouds of your hand and the electron clouds of the table, pushing back against each other across that tiny but ever-present gap. The electrons, he noted, never actually touch, never truly meet, never achieve that final moment of contact that we imagine when we think of one solid thing pressing against another. What feels like touch is actually a kind of hovering, a standing off, a mutual refusal of your electrons and the table's electrons to occupy the same region of space at the same time. This refusal, this stubborn unwillingness of electrons to be compressed together, has a name and a cause, and both of them trace back to one of the most fundamental principles in all of quantum physics, a principle that was first articulated in the city of Hamburg in the year 1925 by a young Austrian physicist named Wolfgang Pauli. Pauli was only 25 years old at the time, but he had already developed a reputation for being exceptionally brilliant and rather unforgiving of sloppy thinking, and it was in that year that he proposed what would come to be known as the Pauli exclusion principle, a rule that governs the behavior of a particular class of particles known as fermions, which includes electrons, protons, and neutrons, among others. The principle states, in its simplest form, that no two fermions can occupy the same quantum state at the same time, which is to say that no two electrons in an atom can have exactly the same set of quantum numbers, the same precise combination of energy level and orbital shape and spin direction that defines their existence within that atom. This might sound like a rather dry and technical rule, the sort of thing that matters only to people who spend their days writing equations on blackboards, but its consequences are anything but dry, are in fact the very reason that you and the table and the floor and the stars themselves are able to exist as solid, stable structures rather than collapsing into undifferentiated smears of matter. Because electrons cannot occupy the same quantum state, they must arrange themselves in shells around the nucleus of an atom, each electron taking up its own unique position in the quantum hierarchy. And when atoms are pushed together, when their electron clouds begin to overlap, the electrons have nowhere to go, cannot simply pile on top of one another, cannot be compressed into the same region of space without violating Pauli's fundamental rule. This creates what physicists call degeneracy pressure, a kind of resistance that arises not from any particular force pushing outward, but simply from the fact that the electrons refuse to be where other electrons already are, refuse to give up their quantum uniqueness, refuse to become indistinguishable from their neighbors. Degeneracy pressure is what keeps matter stable, what prevents atoms from collapsing inward under the pull of their own electromagnetic attraction, what gives substance to the seemingly empty spaces within and between the things you see around you. It is a curious kind of pressure, arising not from motion or heat or any of the usual sources of physical resistance, but from the sheer mathematical impossibility of putting two fermions in the same quantum state, from the structure of reality itself as it exists at the smallest scales. When you press down on a table and feel the table pushing back, you are feeling degeneracy pressure. You are feeling the Pauli exclusion principle made manifest in the form of that invisible cushion of electromagnetic repulsion that keeps your hand from passing through into the wood. The importance of this principle to the stability of ordinary matter was demonstrated mathematically in the year 1967 by two physicists, Freeman Dyson and Andrew Leonard, who published a proof showing that without the Pauli exclusion principle, matter as we know it simply could not exist in its stable, familiar forms. Their proof was lengthy and technical, running to many pages of careful mathematical argument, but its conclusion was striking and clear, namely that the solidity of matter, the fact that objects maintain their shapes and do not collapse or interpenetrate or dissolve into chaos, depends fundamentally on the fermionic nature of electrons and their stubborn refusal to share quantum states. Without Pauli's principle, Dyson and Leonard showed, the attractive forces between positive nuclei and negative electrons would pull matter inward without limit, and everything would collapse into a kind of dense, undifferentiated state. And there would be no tables, no hands, no you, no anything recognizable as the solid world we inhabit. The British physicist Brian Cox, who has spent much of his career explaining physics to general audiences through television programs and public lectures, has often demonstrated and discussed this very phenomenon, pointing out that you have never in your life actually touched anything, that every sensation of contact you have ever experienced has been mediated by this electromagnetic repulsion between electron clouds, that what feels like touch is actually a kind of remote sensing, a detection of forces acting across distances too small to see but too real to ignore. This is not meant to diminish the experience of touch, Cox has noted, but rather to enrich it, to add a layer of wonder to the everyday act of resting your hand on a surface or feeling the texture of fabric against your skin. The world you touch is not a world of direct contact but a world of forces, of fields, of particles communicating across gaps through the language of electromagnetism. And this is, in its own quiet way, rather marvelous. And so as you lie here, perhaps feeling the weight of a blanket against your body, perhaps noticing the softness of the pillow beneath your head, you might take a moment to consider that what you are feeling is not the blanket itself, not the pillow itself, but the electrons of your skin repelling the electrons of the fabric, pushing back against each other across that gap of 1 angstrom, that 0.1 nanometers of space that has always been there and will always be there, that keeps you hovering just slightly above everything you have ever thought you were touching. The sensation is real. The comfort is real. The warmth and softness are real. But they are mediated, translated, carried across that tiny void by the electromagnetic force, by the degeneracy pressure that arises from the Pauli exclusion principle, by the fundamental rules of quantum mechanics that govern the behavior of matter at scales too small for your eyes or fingers to detect. There is something rather peaceful, perhaps, in knowing that you are always hovering, always held at a gentle distance from the world by this invisible cushion of force, always separated from the surfaces around you by a gap so small it might as well not exist and yet so fundamental that without it nothing would be solid, nothing would be stable, nothing would hold its shape against the quiet insistence of entropy and collapse. The table pushes back against your hand not through contact but through communication, through the exchange of virtual photons that carry the electromagnetic force between charged particles, through a process so rapid and so constant that it creates the seamless illusion of solidity, of substance, of one thing pressing against another without any gap at all. Wolfgang Pauli, working in Hamburg all those years ago, could not have known all the ways his principle would come to explain the structure of the world, the stability of atoms, the firmness of the ground beneath your feet, and the gentle resistance of the pillow against your cheek as you settle in for sleep. Freeman Dyson and Andrew Leonard, proving their theorem in 1967, were answering a question that most people never think to ask, namely, why does matter stay together? Why do things keep their shapes? Why does the world not simply fall apart? And Richard Feynman, standing before his audience in 1985, was giving voice to something that had been understood for decades but which still carried the power to surprise. The simple fact that when you touch something, you are not really touching it at all. You are feeling the pushback of electrons that refuse to share their space with the electrons of your skin. This is the invisible pushback, the gentle resistance that shapes every moment of your physical experience. And it is happening right now, between you and the bed, between your hands and whatever they rest upon, between every part of your body and every surface it seems to contact. You are floating, in a sense, suspended on a cushion of electromagnetic force, held at a distance of 1 angstrom from everything around you. And this has always been true. For every person who has ever lived. For every creature that has ever felt the ground beneath its feet or the brush of wind against its skin. The world you touch is a world of forces, of fields, of particles obeying the quiet rules of quantum mechanics, and there is no need to find this unsettling, no need to feel that something has been taken from you by this knowledge. The experience of touch remains, the comfort remains, the solidity remains, and if anything, the understanding of what lies beneath that experience makes it richer, makes it more interesting, makes it a small wonder to contemplate as you drift gently toward sleep. And now we come to a very quiet revolution, one that unfolded across lecture halls and chalkboards over several decades of the 20th century, changing forever our understanding of what matter actually is, though you could be forgiven for never having heard of it. For it happened in the language of mathematics and in the minds of physicists who were themselves still learning how to speak about what they had discovered. This is the story of quantum field theory, and it tells us that beneath everything you see, beneath the chair you might be sitting in, beneath your own hands, beneath the air itself, there lies something like an ocean, or perhaps many oceans layered upon one another. And that everything we call a particle, everything we call matter, is simply a ripple moving across those deep and endless waters. To understand how we arrived at this picture, we must return to the late 1920s, to the work of a young English physicist named Paul Dirac, who was known among his colleagues for his extraordinary silence and his equally extraordinary mathematical intuition. Dirac was troubled by a problem that had been vexing physicists since the quantum revolution began, which was that the new quantum mechanics, as successful as it was, did not account for the effects of special relativity, Albert Einstein's insight that space and time are woven together and that nothing can travel faster than light. The equations that described the electron, that fundamental particle of negative charge that orbits atomic nuclei and carries electrical current through wires. Those equations worked beautifully at low speeds but broke down when electrons moved very fast, as they do in the inner orbits of heavy atoms. Between 1927 and 1930, Dirac set himself the task of finding an equation that would describe the electron while respecting both quantum mechanics and special relativity simultaneously, and what he found was something rather more strange and beautiful than he had anticipated. The Dirac equation, as it came to be known, did indeed describe the relativistic electron, but it also predicted something unexpected. Something that seemed at first like a mathematical error but turned out to be a profound truth about nature. The equation suggested that for every particle, there should exist a corresponding antiparticle, identical in mass but opposite in charge, and within a few years the positron, the anti-electron, was discovered in cosmic ray experiments, confirming Dirac's prediction in the most direct way possible. But there was something else hidden in Dirac's work, something that would take decades to fully appreciate, which was that the electron could no longer be thought of as simply a tiny ball of charge moving through space. Instead, the mathematics suggested that there was an underlying field, spread throughout all of space and time, and that the electron was a particular kind of excitation in this field, a localized disturbance, a wave that had gathered itself into what we perceive as a particle. This idea, that particles are not fundamental but are instead ripples in deeper fields, is the central insight of quantum field theory, and it is worth pausing here for a moment to let this settle, because it represents such a profound shift from our everyday intuition. When you think of a particle, you probably imagine something like a very small ball, a definite object with a definite position, moving through otherwise empty space. But quantum field theory asks us to imagine something quite different. It asks us to imagine that space is not empty at all, but is instead filled with invisible fields, each one corresponding to a different type of particle. There is an electron field permeating all of space, and what we call an electron is simply a place where this field has become excited, where the field has rippled in a particular way. When the electron moves from one place to another, it is not like a ball rolling across a floor, but more like a wave traveling across the surface of a pond, the disturbance propagating through the underlying medium. And there is not just one such field, but many. There is the photon field, which we sometimes call the electromagnetic field, whose excitations are the particles of light that enter your eyes and allow you to see, the same particles that carry radio waves and X-rays and the warmth of sunlight on your skin. There are quark fields, whose excitations bind together inside protons and neutrons, the particles that make up atomic nuclei. There are fields for neutrinos, those ghostly particles that pass through the Earth by the trillions every second without interacting with ordinary matter. And there are fields for heavier, more exotic particles that are created in high-energy collisions and exist for only the briefest instants before decaying. Each type of particle in nature corresponds to its own field, and all of these fields are layered upon one another, occupying the same space, interpenetrating without interfering, like many different oceans somehow coexisting in the same volume. The full mathematical framework for describing these fields and their interactions did not emerge until the late 1940s, and it came through the independent work of 3 physicists working in different parts of the world, each approaching the problem from a slightly different angle, yet arriving at essentially the same conclusions. Julian Schwinger, working at Harvard, developed a mathematically rigorous formalism that was dense and elegant but notoriously difficult to calculate with. Richard Feynman, at Cornell, developed a more intuitive approach based on diagrams that depicted particles interacting by exchanging other particles, little pictures that became a universal language among physicists. And in Japan, Shinichiro Tominaga had been developing his own version of the theory even during the isolation of the war years, working with limited resources and little contact with Western scientists. When the war ended and communications resumed, it became clear that all 3 had solved the same problem, and in 1965 they shared the Nobel Prize in Physics for their development of quantum electrodynamics, the quantum field theory of electrons and photons interacting with each other. Quantum electrodynamics, often called QED, is the most precisely tested theory in all of physics, and its predictions have been confirmed to extraordinary accuracy, to more than 10 decimal places in some cases, which represents an agreement between theory and experiment that is almost unprecedented in science. But what makes QED so remarkable is not just its precision, but what it reveals about the nature of empty space. According to QED, even a perfect vacuum, a region of space from which all matter and all radiation have been removed, is not truly empty. The underlying fields are still there, and they cannot be made perfectly still. Even at their lowest possible energy state, even in what we call the vacuum state, the fields still fluctuate, trembling with what are called zero-point fluctuations, and these fluctuations have measurable physical effects. The first clear evidence for these vacuum fluctuations came in 1947, from an experiment conducted by Willis Lamb at Columbia University. Lamb was studying the hydrogen atom, that simplest of all atoms consisting of just one proton and one electron, and he was measuring the precise energies of different electron orbits. According to the older quantum mechanics, two particular orbital states of the hydrogen atom should have had exactly the same energy, but Lamb found that they did not. There was a tiny shift between them, a discrepancy that could not be explained by any known effect. This shift, which came to be known as the Lamb shift, was quickly recognized as arising from the interaction between the electron and the fluctuating electromagnetic field of the vacuum itself. The electron was being jostled by the invisible ripples of empty space, pushed and pulled by virtual photons that flickered in and out of existence too quickly to be directly observed. And these constant gentle jostlings caused the electron's orbit to smear out slightly, changing its energy by a tiny but measurable amount. The concept of virtual particles is one of the more counterintuitive aspects of quantum field theory, and it is perhaps best to approach it gently, without demanding too much clarity, because clarity is not always available when we venture this far from everyday experience. Virtual particles are disturbances in the quantum fields that arise spontaneously, borrowing energy from the vacuum for times so short that the Heisenberg uncertainty principle permits them to exist without violating conservation of energy. They appear in pairs, a particle and its antiparticle emerging together from nothing, existing for only the briefest instant, and then annihilating each other and vanishing back into the field. You cannot catch a virtual particle or put it in a box, but its effects are real and measurable, for it is these virtual particles that mediate the forces between real particles, carrying momentum and energy from one to another, binding atoms together and keeping the world coherent. Another striking confirmation of these vacuum fluctuations came from a prediction made in 1948 by Hendrik Casimir, a Dutch physicist working at the Philips Research Laboratories in the Netherlands. Casimir realized that if you took two perfectly flat, uncharged metal plates and placed them very close together in a vacuum, there should be a tiny force pushing them toward each other, a force that arose purely from the quantum fluctuations of the electromagnetic field. The reasoning was as follows: between the plates, only certain wavelengths of fluctuation can fit, like standing waves on a guitar string, while outside the plates there is no such restriction. This means there are more modes of fluctuation pushing on the plates from outside than from between them, resulting in a net inward pressure. This Casimir effect, as it came to be called, was extremely difficult to measure because the force is so small. But over the following decades, increasingly precise experiments confirmed that it exists exactly as predicted, providing direct evidence that the vacuum really does seethe with quantum activity. When we speak of empty space seething, we must understand this not as a metaphor but as a literal description. At every point in what appears to be empty space, the quantum fields are fluctuating. Virtual particles are appearing and disappearing. Energy is being borrowed and repaid on timescales too short for us to perceive directly. The vacuum is not a static backdrop against which events unfold, but is itself a dynamic participant in the physics of the universe. Some calculations suggest that if you could somehow add up all the energy contained in these vacuum fluctuations, the result would be enormously, even absurdly large, far greater than all the energy contained in all the matter and radiation in the observable universe. This cosmological constant problem, as it is called, remains one of the great unsolved puzzles of modern physics, a hint that our understanding of the vacuum is still incomplete. But for our purposes tonight, it is enough to know simply that emptiness is an illusion, that what appears to be nothing is in fact something very rich and strange. And what of the particles that make up your body? The electrons that orbit your atoms? The quarks bound inside your protons and neutrons? According to quantum field theory, these are not permanent objects, not tiny billiard balls that have existed since the beginning of time. They are temporary gatherings in the eternal fields, patterns of excitation that persist for a while and then dissipate, ripples that maintain their form as they travel but are never truly separate from the ocean that carries them. The electron in your fingertip is a disturbance in the electron field, and the electron field extends throughout the universe, connecting your fingertip to the most distant galaxies, where other electrons, other ripples in the same field, carry on their own quiet existence. In a sense, all electrons are manifestations of the same underlying field, and what distinguishes one from another is only the location and timing of the excitation, not any fundamental difference in substance. This is a view of matter that is at once humbling and beautiful, and it may be comforting to know that these ideas, strange as they are, have been tested and retested for over 70 years and have withstood every challenge that experimentalists could devise. The mathematical structure of quantum field theory is now understood to underlie not just electromagnetism but all of the fundamental forces of nature, and the fields we have described are woven into the fabric of the universe at the deepest level we have yet been able to probe. When you rest your hand upon a surface, perhaps the worn cotton of a pillowcase or the smooth ceramic of a cup that has long since gone cold, there is a feeling that arises which seems so immediate, so undeniably present, that it would appear absurd to question its authenticity. The sensation of solidity, that reassuring confirmation that the world is real and that you are touching it, feels like the most honest report your body could ever offer you. And yet, as we have begun to see in our gentle wanderings through the spaces between atoms, what you feel as touch is not the simple meeting of matter with matter that intuition would suggest. Instead, it is something far more interesting, and in its own quiet way, far more beautiful. It is a construction, a careful interpretation assembled within the soft folds of your brain, built from electrical whispers that travel along delicate neural pathways, arriving milliseconds after the electromagnetic events that inspired them. The solidity you feel is, in the most tender and precise sense of the word, an illusion, though it is an illusion so useful, so seamlessly woven into your experience of being alive, that it deserves to be understood rather than dismissed. To appreciate how this illusion comes to be, we might first consider what actually happens at the boundary where your skin approaches another surface. We have already spoken of the electron clouds that surround all atoms, those diffuse regions of probability where negatively charged particles exist in their uncertain way, and we have seen how these clouds repel one another through the electromagnetic force, creating what might be thought of as an invisible cushion between all objects. When your fingertip draws near to a tabletop, the electrons in your skin and the electrons in the wood begin to push against each other, not through direct contact but through the fundamental repulsion that like charges exert upon one another. This repulsion is what creates the sensation of resistance, of something being there, of a boundary that cannot be crossed. But your brain does not receive information about electromagnetic fields or quantum mechanical interactions. Instead, it receives only the signals that your sensory receptors choose to send, and these signals are themselves a kind of translation, a conversion of physical forces into the electrochemical language that neurons speak. Beneath the surface of your skin, distributed throughout the epidermis and the deeper tissues below, there exist specialized sensory structures that have evolved over countless generations to detect mechanical deformation. Among these are the Merkel cells, which cluster in the ridges of your fingerprints and respond to sustained pressure, providing the detailed information that allows you to feel the edges and textures of objects you hold. There are also the Pacinian corpuscles, larger structures buried deeper within the skin, wrapped in onion-like layers of connective tissue that make them exquisitely sensitive to rapid vibrations and sudden changes in pressure. When you run your finger across a surface and feel its roughness or smoothness, it is these receptors, along with others such as Meissner corpuscles and Ruffini endings, that are converting mechanical forces into electrical signals. What they detect is not contact in any absolute sense, but rather the compression and deformation of tissue, the bending and stretching of cellular membranes that occurs when electromagnetic repulsion creates what we perceive as pressure. They are measuring force, not touch, and the distinction is subtle but important. Once these receptors have been activated, their signals must travel to the brain, and this journey, though swift by everyday standards, is not instantaneous. Sensory information from your fingertips travels along nerve fibers at speeds that vary depending on the type of fiber involved, with the fastest myelinated axons carrying signals at roughly 80 meters per second, while slower unmyelinated fibers may transmit at considerably lower rates. The neuroscientist David Eagleman, whose work has illuminated many of the hidden processes underlying perception, has explored how these transmission times shape our experience of the present moment. By the time a signal from your fingertip reaches the somatosensory cortex, that strip of neural tissue running across the top of your brain like a headband from ear to ear, somewhere between 20 and 100 milliseconds may have elapsed, depending on the length of the neural pathway and the complexity of the processing involved. This means that every tactile sensation you experience is, in a very real sense, a report from the past, a bulletin about something that has already happened by the time you become aware of it. You are never touching the present moment, only receiving news of what occurred a fraction of a second ago, though the delay is so consistent and so seamlessly incorporated into your experience that you never notice the lag. The somatosensory cortex itself is organized in a manner that reflects the body's surface, with different regions dedicated to processing information from different parts of your skin. The representation is not proportional to physical size but rather to sensitivity, so that your lips and fingertips, which are densely packed with receptors, occupy far more cortical territory than your back or your thighs, which have comparatively few. When signals arrive in this region, they do not simply produce a direct readout of what is happening at the skin but are instead processed, compared, integrated with other information, and ultimately interpreted according to expectations and prior experience. This is where the construction of tactile experience truly begins, and it is here that we encounter one of the most profound ideas in the science of perception, an idea that traces its origins to the 19th century and the work of the German physician and physicist Hermann von Helmholtz. Helmholtz, working in an era before the tools of modern neuroscience existed, nonetheless arrived at insights that remain central to our understanding of how the brain creates the world we perceive. He proposed that perception is not a passive reception of sensory data, but rather an active process of inference, in which the brain uses incomplete and often ambiguous information from the senses to construct a hypothesis about the state of the external world. He called this process unconscious inference, recognizing that we are not aware of the calculations and assumptions that underlie our perceptions, only of the finished product that emerges into consciousness. When you feel the solidity of a surface beneath your palm, your brain is not simply registering raw sensory data but is instead making educated guesses, filling in gaps, and applying learned expectations about how surfaces typically behave. The sensation of touch is, in Helmholtz's framework, a kind of best guess, a probabilistic conclusion drawn from limited evidence. This constructive nature of touch has been demonstrated in remarkable ways by modern experiments, perhaps none more striking than the rubber hand illusion first formally documented by the psychologists Matthew Botvinnik and Jonathan Cohen in 1998. In this experiment, a participant's real hand is hidden from view behind a screen while a realistic rubber hand is placed in front of them, positioned where their own hand might naturally rest. The experimenter then uses two small brushes to stroke both the rubber hand and the participant's hidden real hand simultaneously, matching the timing and location of each stroke as precisely as possible. After only a few minutes of this synchronized stimulation, something curious begins to happen. The participant starts to feel as though the rubber hand is their own, experiencing the touch of the brush on the rubber surface as though it were occurring on their actual skin. When the experimenter suddenly threatens the rubber hand with a hammer or a sharp object, participants often flinch, their bodies responding as though the artificial hand were genuinely part of them. What this experiment reveals is that the brain's sense of where touch occurs, and indeed of where the body itself exists in space, is not fixed or certain but is instead continuously constructed from available sensory evidence. When the visual information suggesting ownership of the rubber hand is consistent with the tactile information arriving from the real hand, the brain revises its model of the body, incorporating the fake hand into the felt sense of self. The implications of such findings extend far beyond laboratory curiosities, touching upon deep questions about the nature of conscious experience and the relationship between the brain and the world it inhabits. The philosopher Thomas Metzinger has explored these questions with particular care, developing a comprehensive account of how the brain creates what he calls the phenomenal self-model, the internal representation that gives rise to the feeling of being a self situated in a body moving through a world of solid objects. In Metzinger's view, conscious experience is something like a user interface, a simplified and highly processed representation that hides the underlying computational complexity of neural processing, much as the icons on a computer screen hide the intricate workings of silicon and electricity beneath. The solidity you feel when you touch a surface is part of this interface, a useful fiction that allows you to navigate and interact with your environment without needing to understand the electromagnetic forces and quantum mechanical principles that actually govern the interaction. Your brain does not show you the truth of what is happening at the atomic level because such information would be neither useful nor comprehensible in the context of everyday survival. Instead, it shows you a world of solid surfaces and distinct objects, a world that makes sense and invites action, even though this world is, at bottom, a carefully edited representation. This notion that consciousness presents us with a simplified and somewhat fictional version of reality finds additional support in the work of the philosopher and cognitive scientist Daniel Dennett, who has proposed what he calls the multiple drafts model of consciousness. According to this model, there is no single moment at which sensory information becomes conscious, no central theater where the finished perception is displayed for an inner observer. Instead, the brain continuously generates multiple parallel interpretations of incoming data, revising and updating these interpretive drafts as more information arrives. The version that eventually influences behavior and memory is not a raw, unfiltered feed from the senses, but rather a heavily processed narrative, edited for coherence and consistency. When you touch something and feel its solidity, What you experience is not the immediate report of receptors firing, but rather the outcome of this ongoing editorial process. A draft that has been revised and finalized into something that feels seamless and present, even though it is built from fragments arriving at slightly different times and processed through multiple stages of neural interpretation. And so we arrive at an understanding of touch that is perhaps gentler, more humbling, and more wondrous than the naive intuition with which we began. The sensation of solidity, so familiar and so trusted, is a story your brain tells you about electromagnetic events occurring at scales too small to see and traveling along pathways too swift to notice. The pressure you feel is not the meeting of matter with matter, but the compression of tissue in response to forces that arise from the invisible dance of electrons. The present moment you seem to inhabit is not truly present, but is rather a reconstruction of the very recent past, assembled from signals that traveled at finite speeds and were processed through layers of neural interpretation. The body you feel as your own is not a fixed and certain thing, but a model continuously updated according to the available evidence, capable of being fooled, as the rubber hand illusion demonstrates, when that evidence is cleverly manipulated. And the solid world around you, the surfaces and objects that seem so undeniably there, are in some deep sense creations of your brain, useful fictions designed to help you navigate a reality that is far stranger and far more beautiful than the everyday experience of touch would ever suggest. This is not cause for alarm or distress, but rather an invitation to rest in the quiet marvel of how much work your brain does on your behalf, constructing a world that feels coherent and trustworthy, allowing you to move through life with confidence even though the foundations of that confidence are themselves a kind of artful simplification. The illusion of solidity serves you well, keeping you safe, guiding your hands to grasp what needs grasping and to release what ought to be let go. And as you lie here now, perhaps feeling the gentle weight of blankets upon your body or the soft support of a pillow beneath your head, you can appreciate that these sensations, so comforting and so real, are the brain's gift to you, a tactile story told in the language of neurons, about electromagnetic events that will forever remain just beyond the reach of direct experience. And so we come to understand that this principle, this gentle refusal of matter to ever truly meet itself, extends far beyond the modest scale of fingertips and tabletops, reaching outward to encompass the vast and unhurried machinery of the cosmos itself, where stars and planets drift through the darkness in their ancient orbits, and where even the most violent events imaginable are still, at their deepest level, governed by the same electromagnetic negotiations that prevent your hand from passing through a pillow. When we speak of celestial collisions, of worlds meeting or stars merging, we are using language that our everyday experience has shaped, language built from watching billiard balls click together or raindrops splash against windows. But the reality at cosmic scales remains faithful to the same quantum principles we have been exploring here in this quiet hour. A planet does not collide with another planet in the way that we might imagine two stones meeting in a stream, for the electromagnetic fields of each body begin their conversation long before any notion of contact could occur. And what follows is a complex exchange of forces, a redistribution of matter and energy that happens through the medium of fields rather than through any direct touching of substance to substance. The atoms of one world repel the atoms of another even as gravity draws them near, and the catastrophic rearrangements we call collisions are really electromagnetic interactions of staggering intensity, yet still interactions across those same quantum voids that exist between all things. In August of the year 2017, the Laser Interferometer Gravitational Wave Observatory, which carries the rather more comfortable abbreviation of LIGO, detected something that astronomers had theorized about for decades but had never before witnessed directly, which was the merger of two neutron stars in a galaxy some 130 million light-years distant, an event catalogued with the designation GW 170817, a name that carries within it the date of that detection like a small historical marker. Neutron stars are among the densest objects in the known universe, the collapsed cores of massive stars that have exhausted their fuel and fallen inward under their own gravity until the protons and electrons of their atoms have been crushed together to form a sea of neutrons packed so tightly that a single teaspoonful would weigh several billion tons if you could somehow transport it to an earthly kitchen. Which you could not. But the comparison helps the mind to grasp the extraordinary compression involved. And yet even in these extreme environments, where gravity has done its utmost to force matter into the smallest possible volume, there exists a pressure that resists further collapse, a quantum mechanical stubbornness that arises from the behavior of neutrons themselves and their refusal to be pushed into identical quantum states. This is a manifestation of what physicists call degeneracy pressure, and it is the final defense of matter against the overwhelming inward pull of gravity, a defense that holds firm until the mass exceeds certain limits, at which point even this quantum resistance is overcome and the star collapses further into something stranger still, perhaps a black hole, where our current understanding grows uncertain and our language begins to fail us. The story of degeneracy pressure and its relationship to stellar stability is one that carries a certain biographical charm, for it was worked out in significant detail by a young man named Subrahmanyam Chandrasekhar while he was aboard a ship traveling from India to England in the year 1930. A journey that took several weeks and provided the 19-year-old student with ample time to calculate and contemplate. There on the gentle swells of the ocean, as the steamship carried him toward graduate studies at Cambridge, Chandrasekhar applied the principles of quantum mechanics and special relativity to the question of how white dwarf stars, which are another type of stellar remnant, maintain their structure against gravitational collapse, and he arrived at a remarkable conclusion. White dwarf stars, which represent the final state of stars similar to our own Sun after they have exhausted their hydrogen and helium fuel, are supported against gravity not by the heat of nuclear fusion, which has ceased, but by the pressure exerted by their electrons, which resist being compressed into identical quantum states, a phenomenon that arises from the same Pauli exclusion principle that gives structure to atoms and prevents your chair from absorbing you into its cushions. Chandrasekhar demonstrated through his calculations that this electron degeneracy pressure can support a white dwarf only up to a certain mass, approximately 1.4 times the mass of our Sun, and beyond this limit, which now bears his name as the Chandrasekhar limit, the electrons would need to move at speeds exceeding the speed of light to provide sufficient pressure, which is not permitted by the laws of physics, and so the star cannot remain a white dwarf but must collapse to something denser. This limit of 1.4 solar masses, determined by a young man on a sea voyage nearly a century ago, remains one of the fundamental numbers in astrophysics, a boundary written into the fabric of reality by the quantum behavior of electrons, those same electrons whose refusal to overlap prevents your morning coffee from falling through your cup. The stars themselves are governed by the same principles that govern the small and the everyday, and the universe maintains its consistency across scales that range from the subatomic to the galactic, a consistency that is rather reassuring when you settle into your pillow and allow your thoughts to wander. And when we turn our attention back from the dramatic deaths of stars to the quieter processes that occur within more modest assemblies of matter, we find that what we call chemical bonds, the connections that hold molecules together and give substances their properties, are themselves manifestations of this same electromagnetic relationship between atoms that never quite touch. A chemical bond is not a tiny rod or spring connecting two atoms like balls on a molecular model kit, though such models are useful for certain purposes, but rather a shared arrangement of electrons, a region of space where the electron clouds of two or more atoms overlap and mingle, creating a configuration of lower energy that holds the atoms in proximity to one another. The detailed understanding of how this sharing works, how electrons can be distributed across multiple atoms to create stable molecules, was developed with particular clarity by the American chemist Linus Pauling, whose work on the nature of the chemical bond, published in a series of papers beginning in 1931 and later gathered into an influential textbook, provided the theoretical framework that chemists still use to understand molecular structure. Pauling introduced concepts such as electronegativity, which describes how strongly different atoms attract shared electrons, and he developed methods for predicting the shapes and properties of molecules based on the quantum mechanical behavior of their constituent particles. His work earned him the Nobel Prize in Chemistry in 1954, and it demonstrated that the world of chemistry, with all its rich diversity of substances and reactions, emerges from the quantum electromagnetic interactions of atoms that hover near one another without ever achieving contact. Every molecule in your body, every protein that folds into its functional shape, every strand of DNA that carries the instructions for building and maintaining you, exists by virtue of these shared electron arrangements, these quantum electromagnetic partnerships between atoms that remain always slightly apart. The processes of life, which might seem from a distance to be mechanical or hydraulic in nature, are at their foundation a continuous dance of electromagnetic interactions, a choreography of fields and forces that operates according to the same principles whether it occurs in a simple chemical reaction in a laboratory flask or in the intricate molecular machinery of a living cell. Consider the enzymes that catalyze the reactions keeping you alive in this very moment, the molecules that allow your cells to extract energy from food and build new structures from raw materials and repair damage when it occurs. These enzymes work by bringing other molecules into close proximity and precise alignment, positioning them so that their electron clouds can interact in ways that would be far less probable if the molecules were simply floating freely in solution. The enzyme does not push the molecules together in any mechanical sense, for there is nothing solid to push with, but rather creates an electromagnetic environment that guides and stabilizes the transition of electrons from one arrangement to another, facilitating the making and breaking of chemical bonds with an elegance that human technology has yet to match. And DNA replication, that fundamental process by which your genetic information is copied each time a cell divides, is similarly a quantum electromagnetic phenomenon, a process in which the double helix unwinds and new nucleotides are positioned alongside each exposed strand, their electron clouds interacting with the electrons of the template strand in patterns determined by the laws of quantum mechanics, patterns that ensure with remarkable fidelity that adenine pairs with thymine and guanine pairs with cytosine, preserving the sequence of information through countless generations of copying. There is a curious fact about the physical continuity of your body that emerges from this understanding of matter as fields and forces rather than solid substance, which is that the atoms comprising you are not permanent fixtures but rather temporary participants in the pattern that is you, passing through your body over the course of years as old atoms are exhaled or excreted and new atoms are incorporated from the food you eat and the air you breathe. Various estimates suggest that most of the atoms in your body are replaced over a period of roughly 7 to 10 years, with some tissues turning over more quickly and others more slowly, But the general point remains that the physical substance of which you are made is in constant flux, a river of matter flowing through the persistent shape that you recognize as yourself. This raises questions that the philosopher Derek Parfit explored with considerable depth in his writings on personal identity and what he called the relation of physical continuity. If the atoms that compose you today are largely different from the atoms that composed you a decade ago, in what sense are you the same person? And what exactly is it that persists through this material turnover? Parfit suggested that our ordinary notions of personal identity may be less substantial than we commonly assume, that what we call the self is perhaps better understood as a pattern of psychological continuity, a series of connected mental states and memories, rather than as a single enduring thing that remains constant through time. These are deep waters that we need not swim in too vigorously at this quiet hour. But the questions themselves arise naturally from the physics we have been considering, from the recognition that matter is not the solid stuff we intuitively imagine, but rather a temporary condensation of fields, a transient arrangement of forces that holds together for a while and then disperses. You are, in a sense that is both poetic and rigorously physical, a pattern in the electromagnetic field, a coherent organization of forces that maintains its structure through time even as the specific particles participating in that structure come and go. The boundaries of your body, which seem so definite when you look in a mirror or feel the pressure of the floor beneath your feet, are themselves patterns of electromagnetic interaction. Regions where the forces associated with your atoms meet the forces associated with everything else and negotiate their mutual arrangement according to laws that permit proximity but not contact. And this is perhaps the gentlest way to understand the truth that you can never truly touch anything, which is to recognize that touching was never really what you thought it was. That the sense of solidity and contact that you experience is the feeling of electromagnetic fields meeting and resisting one another, a feeling that is every bit as real and meaningful as any alternative could be. You have been touching things all your life, and that touching has always been this, has always been the dance of fields and forces across infinitesimal gaps. And knowing this need not diminish the experience but can instead reveal a deeper appreciation for the extraordinary processes that create your ordinary world. We are all of us patterns in fields, temporarily coherent assemblies of forces that have come together for a while to experience the universe from a particular point of view, and though we never quite achieve the solidity we imagine ourselves to possess, we are no less real for that, and no less present in this moment, as you rest quietly and allow these thoughts to settle like gentle dust into the comfortable furniture of your mind, and the boundary between you and your pillow remains as it has always been, an electromagnetic conversation that requires no resolution, only the peaceful continuation of forces in their ancient and unhurried balance. And so we arrive at a kind of resting place, a gentle plateau from which we might look back across the terrain we have wandered together, and perhaps see it differently now, softened by all we have learned, transformed by the quiet revelations that have accumulated like morning dew gathering on grass. We have spoken at length about emptiness, about the vast spaces that exist between things, about the quantum void that separates what we thought was touching. And it would be natural, perhaps, to feel a kind of loneliness in this knowledge, a sense of isolation that comes from understanding that your hand has never truly pressed against another hand, that your lips have never quite met the skin of someone you love, that all contact is mediated by invisible forces acting across unbridgeable distances. But this interpretation, while understandable, misses something essential, something that the deepest thinkers in physics and philosophy have recognized, which is that emptiness, properly understood, is not separation at all, but rather the very medium of connection, the shared ground upon which all existence rests, the common sea in which every particle, every field, every manifestation of matter floats together in an endless, gentle communion. The Italian physicist Carlo Rovelli, who has spent decades contemplating the nature of reality at its most fundamental level, writes about quantum mechanics with a kind of poetry that is unusual in scientific discourse, and he has developed a perspective known as relational quantum mechanics that offers us a particularly beautiful way of understanding our situation. In Rovelli's view, the properties of things do not exist in isolation, waiting to be discovered, but rather emerge only in relationship, only in the interactions between one system and another, one observer and another, one quantum field and another. A particle does not possess a definite position until it relates to something else. A spin does not point in a particular direction until it is measured by another system. And even the most basic qualities we might attribute to matter turn out to be relational, dependent, woven into the fabric of interaction. This is not a deficiency or a limitation, but rather a profound statement about the nature of existence itself, which is that nothing exists in complete independence. Nothing stands alone. Everything is defined by its relationships to everything else. And the emptiness between things is not a void that separates, but rather the space in which relationship becomes possible, the medium through which connection unfolds. Rovelli has written that the world is not a collection of things, but rather a network of interactions, and that we ourselves are not observers standing outside this network, but participants within it, nodes in an infinite web of relations that extends outward in every direction, backward and forward through time, connecting us to distant galaxies and ancient stars and quantum fluctuations that occurred in the first moments after the universe began. The emptiness we have described, the quantum void between your finger and this page, between one atom and the next, between the electrons in your neurons and the proteins they influence. This emptiness is the same emptiness that exists between stars, between galaxies, between the most distant objects we can observe and those closest to us. And it is all continuous, all connected, all part of the same vast expanse of spacetime in which the quantum fields dance their eternal dance. You are not separated from the universe by the emptiness within you. You are connected to it, embedded in it, continuous with it. And the boundaries you perceive between yourself and everything else are, from the perspective of quantum field theory, largely illusory, convenient fictions that help us navigate daily life but do not represent the deeper reality of what we are. It is remarkable, and worth pausing to appreciate in this gentle way, that insights so similar to these were articulated thousands of years ago by Buddhist philosophers who had no knowledge of quantum mechanics, no particle accelerators, no mathematical formalism with which to describe the behavior of subatomic particles. The concept of sunyata, often translated as emptiness or voidness, is central to Buddhist thought, particularly in the Madhyaka tradition associated with the philosopher Nagarjuna, who lived in India around the 2nd century of the Common Era. Sunyata does not mean nothingness in a nihilistic sense, does not suggest that the world is unreal or that our experiences are meaningless, but rather points to the absence of inherent, independent existence in all phenomena. Everything that exists, according to this understanding, exists in dependence on other things, arises through conditions and causes, and has no essential nature that can be separated from its relationships to everything else. This is strikingly similar to what Rovelli and other quantum physicists have concluded through entirely different methods, through mathematics and experiment rather than meditation and philosophical analysis. and the convergence is fascinating to contemplate. The physicist Fritjof Capra, in his influential book The Tao of Physics, published in 1975, explored these parallels in careful detail, examining the ways in which modern physics, and quantum mechanics in particular, seemed to echo the insights of Eastern mystical traditions. Capra noted that the emptiness of sunyata, the Buddhist understanding that all things are empty of independent existence, corresponds remarkably well to the quantum mechanical picture of matter as patterns of energy, as excitations in underlying fields, as processes and interactions rather than solid, permanent, independently existing things. The atoms that make up your body, Capra observed, are not tiny billiard balls bouncing off each other but rather dynamic patterns, probability clouds, nodes in a vast network of quantum fields that extends throughout all space and time. When Buddhist teachers speak of the interconnectedness of all phenomena, of the way in which nothing exists in isolation, they are describing, in their own language and from their own perspective, something very close to what physicists describe when they speak of quantum entanglement, of field theory, of the relational nature of quantum properties. The emptiness is the connection, the void is the medium of unity, and what seems at first like separation turns out, on closer examination, to be the deepest form of togetherness. The astronomer Carl Sagan, whose voice has soothed and inspired countless people seeking to understand their place in the cosmos, often spoke of the connection between human beings and the universe in ways that resonate deeply with these ideas. Sagan reminded us that we are made of star stuff, that the carbon in our cells, the oxygen in our blood, the iron at the core of each hemoglobin molecule, all of these elements were forged in the hearts of ancient stars that lived and died billions of years before our solar system formed. The atoms in your left hand may have come from a different star than the atoms in your right hand, Sagan observed, and yet here they are, brought together by gravity and chemistry and the long unfolding of cosmic evolution, assembled into the intricate pattern that is you. But we can go even deeper than this, as we have learned, because the atoms themselves are not the fundamental constituents of your being, and what truly makes you up is not matter in the old-fashioned sense but rather excitations in quantum fields, ripples in the electron field and the quark field and the other fields that permeate all of space. The electron field in your hand is not separate from the electron field in a distant galaxy. There is only one electron field, extending throughout the entire universe, and the electrons in your neurons are excitations in the same field as the electrons in the most remote star we can observe. You are not merely made of star stuff, you are continuous with it, woven into it, a local pattern in a universal tapestry that has no edges, no boundaries, no true separations. The same emptiness that we have explored within the atom, the quantum void that prevents true contact, extends outward in all directions, filling the space between planets and stars and galaxies, and it is all the same emptiness, all part of the same quantum vacuum with its virtual particles flickering in and out of existence, its zero-point energy humming at every location, its fields ready everywhere to be excited into the particles we observe. When you look up at the night sky, if you are fortunate enough to be somewhere dark enough to see the stars, you are looking through this emptiness, and it connects you to everything you see. Light from distant suns travels through the same quantum fields that fill your living room, the same vacuum that exists between the atoms in your eyes. And when that light arrives and excites the electrons in your retina, it is a communication across the void that reveals the void to be no barrier at all, but rather the universal medium of connection. Astronauts who have traveled beyond Earth's atmosphere have reported experiences that speak directly to this sense of connection, this awareness of being part of something vastly larger than oneself. Edgar Mitchell, who walked on the Moon during the Apollo 14 mission in 1971, described what has come to be known as the overview effect, a profound shift in awareness that occurred as he gazed back at Earth from space. Mitchell reported an overwhelming sense that everything was connected, that the boundaries he had always assumed between himself and the world, between nations and peoples, between humanity and the cosmos, were in some fundamental sense illusory. He felt, he said, a kinship with the stars and the planets, an understanding that he was not separate from the universe but was the universe, a particular and temporary expression of the same processes that had created everything he could see. This was not a mystical experience in the sense of being divorced from reason, but rather an experimental apprehension of what physics had been telling us all along, that we are embedded in the cosmos, continuous with it, made of the same fields and forces that fill all of space and time. Other astronauts have reported similar experiences, this sense of profound connection that comes from seeing Earth from the outside, from gaining a perspective that reveals the arbitrary nature of the boundaries we draw on maps and in our minds. Richard Feynman, whose insights into quantum electrodynamics have illuminated so much of what we have discussed tonight, reflected in 1955 on what physics reveals about the universe, and his words are worth considering as we approach the end of our contemplation. Feynman observed that our imagination is stretched to the utmost by physics, not as in fiction by imagining things that are not really there, but by comprehending things that are there, a universe of great range and complexity. The quantum world we have described, with its probability amplitudes and virtual particles and fields that extend through all space, is not a fantasy but a reality, confirmed by experiment after experiment, by technologies that work only because quantum mechanics is true, and yet it is stranger than almost anything we might have invented had we not been forced to confront the evidence of nature. The emptiness we have explored is real. The void between you and everything you touch is real. And yet this reality, far from diminishing us, reveals us to be part of something far more interconnected, far more subtle, far more beautiful than the solid mechanical world we once imagined ourselves to inhabit. And so we come to rest with a new understanding, a gentle revision of what emptiness means. The quantum void is not absence but presence, not separation but the condition for relationship, not nothing but a sea teeming with potential, with virtual particles, with the fluctuations from which all observable reality emerges. You are floating in this sea, as is everyone you have ever known, as is every star and galaxy and distant quasar, and the sea is continuous, unbroken, extending in all directions through space and backward and forward through time. When you reach out your hand, electromagnetic fields extend from your electrons to meet the electromagnetic fields of whatever you are reaching toward, and these fields blend and push and influence each other across the quantum void. And though you do not touch in the old solid mechanical way you once imagined, you are nevertheless in contact, in communication, in relationship. The emptiness is not a wall between you and the world, but rather the medium through which you are forever connected to it. This is perhaps the gentlest of all the truths physics has to offer, the recognition that our apparent isolation is an illusion of scale, a trick of perception, a failure to see deeply enough into the nature of things. At the quantum level, there are no isolated objects, no independent substances, only fields and interactions, only patterns and processes, only relations extending outward to encompass everything that exists. You are not alone in the void. You are the void. You are an expression of it, a way it has found to know itself, to experience itself, to contemplate itself in the quiet hours before sleep. The emptiness between your atoms is the same emptiness between the stars, and it holds everything together in a vast and silent embrace, cradling all matter, all energy, all existence in its gentle depths. As your breathing slows and your thoughts begin to soften and drift, perhaps this image can accompany you into sleep, the image of a universe that is mostly empty and yet through that very emptiness achieves its deepest connections. The quantum fields that make up your being extend outward without boundary, continuous with the fields that make up everything else. And in this continuity there is a kind of rest, a release from the burden of separation, a homecoming to the truth that you have always been part of the whole, floating together with all things through space-time, embraced by the emptiness that is not absence but rather the condition for everything that exists, the quantum sea in which we all belong.